Hello and welcome back. So today I'm going to continue working on my effect pedal by actually making an effect for it. And based on the votes I've gotten from you guys, I'm going to be building the sustain effect. So what I want to do today is look at how this effect is supposed to work, what is the principle behind it, try to simulate it, and then build it and see what happens. So if you're curious, then keep watching. So let's start off with understanding what is this effect supposed to be doing. Now, when you're playing an instrument, a guitar or anything else, and you strike one of the chords, you'll get a peak amplitude, and then this amplitude slowly fades away. This is because the mechanical energy that was stored in the string when you struck it is slowly being dissipated and exchanged with the environment. Now, from a signal point of view, this looks like a logarithmic decay. So you have a peak amplitude at the beginning, and then this slowly fades away in time. Now, when you're playing a song that has a lot of pauses in between the notes, so you strike one chord at a time and then you wait a minute, you will get a lot of volume variations. So you'll have peak volumes and then these decay away, and then you have another peak and so on. So this is something that you might not want to have. And to counteract this effect, you have the compression sustain effect. Basically what this effect does is it keeps the volume constant regardless of the input signal amplitude. Now, if this behavior sounds familiar, basically it's because the same principle is applied in automatic gain control circuits in radio receivers. There, regardless of the strength of the signal coming from the radio station, after this amplifier stage, the output signal is always constant. So when you turn from one radio station that has a very strong signal to a radio station that has a very weak signal, you don't want to hear this amplitude difference in the volume. So this automatic gain control circuit keeps the volume always constant. And basically the same thing is what we want with our guitar effect. So the way in which this circuit is supposed to be working is that you have an input signal, it goes through a voltage controlled amplifier, so an amplifier that can change its amplification based on an input voltage signal, so this gain setting signal, and then you have the output, and now you take the output, you add a peak detector, so you're only interested in the peak of the signal, you're not really interested in anything else about the signal. You compare this to a reference voltage, so this reference would be the exact amplitude that you want at the end, and you're providing negative feedback by setting the gain. Basically, what you want is to have a circuit that takes any sort of signal amplitude, so highs and lows doesn't really matter, and at the output provides a constant amplitude signal. Now, the exact amplitude can be set, but the point is that it has to be constant, so it shouldn't change with the input signal. And the component that I'll be using to perform this variable gain function is an operational transconductance amplifier. Now, with a normal operational amplifier, basically you have two inputs, positive and a negative input, and an output, and the relationship between the input and the output is that the output voltage is equal to the difference between the input voltages times the gain of the amplifier. So with a normal operational amplifier, this is a very high value. Now, with an operational transconductance amplifier, the difference is that although you still take the input voltages into account, the output is now a current. So you're setting the output current based on the input voltages and the gain of the transconductance amplifier, which is called its transconductance. Now, as with the operational amplifiers, the transconductance of such an amplifier is usually a constant. But you do have certain components that have this transconductance variable, and you can set it with an external pin from which there is a certain relationship to your transconductance. So the transconductance of the amplifier is variable defined by this input signal. Now, although this is an input current, if you add a resistor in series and you apply a voltage, based on what voltage you're applying, you will be able to set a certain current, so a certain gain. Now, as actual components to use, most of the old schematics where you had sustain effects went with either the CA3080 or the BA662. But these components, of course, are obsolete nowadays, so you can rarely find them. There is, of course, alternatives. Two of the ones that I found are the LM13700 and the LT1228. And for today's project, I'll be going with the LM13700, which is also quite a cheap component. But another advantage about this is that based on what information I could find on the internet, it's basically a copy of the CA3080 and with some extra components added. So the basic voltage controlled amplifier that I'll be using will be this one. Now, before moving on to the actual circuit, there's one more thing that needs to be mentioned. And that is that, unlike a clean sine wave, the sound coming from the guitar when you play a note is a combination of multiple sine waves that end up being a non-symmetrical signal. So when you reference a normal sine wave around its average point, you will have two symmetrical signals, which are granted phase shifted, but the two peak amplitudes are equal. Now, if you take a signal that's a combination of multiple other single frequency sine waves, you can end up with the case in which the two amplitudes are not equal. And of course, you will not know which is the highest amplitude, so you can't make a circuit that only looks at the positive or the negative amplitude. For our sustain effect, we will need a peak detector that can look at both peaks and then decide which has the highest absolute value and take that signal into account to adjust the gain. So let's look at how the circuit would work in a simulation first. So what I got here is the basic circuit that I'll be building today. On the left side we have the transconductance amplifier, the input and the output, and on the right side we have the peak detector circuit. So if we compare the left side with the typical application from the datasheet, we see our input signal coming into the positive input. The negative input is connected to ground, so is the positive through two 500 ohm resistors. Now in the typical application, here we have a 1 kilo ohm variable resistor, and that is what I'll be using in my actual project. The variable resistor is important for offset compensation. We have this diode pin connected to the positive supply, so in the application it's 13 kilo, I used 20 kilo ohms. The exact value influences the maximum gain, but also the linearity. And then we have our output connected to ground through a 47 kilo ohm resistor, and this feeds back into the buffer circuitry, so these two Darlington transistors, and then the output goes directly to the output, so this will couple into the second board, but it also feeds into this secondary circuit. What we have here, we have the first transistor that simply takes our input signal and provides a non-inverted and an inverted output, so the two signals are in phase opposition. These are detected by the two transistors, so Q2 and Q3, and basically these provide our peak detector with the threshold voltage, 0.6 volts for the base emitter voltage. So if either of the two signals is large enough to polarize the transistor, then the collector will be pulled to ground. And now the voltage potential of the collector of these two transistors is responsible for driving the final transistor, which in turn is providing our voltage to the first circuit, so to provide the negative feedback to the gain setting. If there's no signal in the two transistors, then the base of the fourth transistor is connected directly to the positive supply, so there's a maximum output voltage going to set the gain, so we have the maximum gain. The more signal is applied to the two transistors, then the base is pulled lower and lower, and then the feedback voltage is also lowered. So if we run this thing, I'm simulating with this sort of signal, so we have a maximum initial amplitude and then this decays down in time. And if we look at the output, and we just split the two into two windows, we can see that the output is maintained at a constant amplitude for as long as the amplifier can provide enough gain, and then this also decays after a while. We can also look at our inverting circuitry. So what I plotted here is our input signal and the two output signals. And if we zoom in, we can see that our input signal is perfectly in phase with the non-inverted signal, but it's in phase opposition with the inverted signal. So we can have a look at both of the peaks. One more thing to look at is how our feedback current is influenced by the input signal. So I've plotted in my input signal, and if we look at the feedback current, we can see that we have a steep drop as the input signal is applied to the circuit, and then this returns back to maximum as the input signal is dying down. So we can see this feedback signal providing our negative feedback to stabilize the system. So it looks really nice in the simulation, but let's see if it actually works in real life. Now, before starting to build this thing, especially with this sort of complex designs where you have multiple boards interconnected, it's important to make sure that the boards actually fit together. So based on the designs that we did in our previous videos, I made little paper cutout of the final size of the board, or the size of the board that we were expecting to have for the effect. Now, if we look at it in our final effect circuit and we try to put it in, we can see that it lines up with the spacers quite nicely, but it doesn't really line up with our interboard connector. So even if I tighten out the paper like this, we can see that we have an offset of about 1 centimeter. So there's two causes for this. First of all, our board is at an angle, so in our initial design the board was nice and perpendicular, but because of reasons really, the board is sitting at an angle, so that is pulling the connector a bit to the side. But it's also because of my estimation skills. They're not very good. So what I'll have to do is increase the board size a bit so that the connector can actually get onto the board so we can have our interconnections. And because of the increased board size, one of the other things that I had to do was to make these capacitors much smaller. So here you can see that I already placed in my new low profile capacitors. These are a couple tantalum capacitors. Previously these were large electrolytic capacitors, so they were very tall and they were too close to the second board, so they would end up hitting, and that would not be a good thing. Now, before moving on, I would just like to show you some of the modifications that I've brought to the motherboard circuit. So the first board that was built during this project, basically the topic that I wanted to address was the noise of the circuit. So first of all, I reduced the input resistor from 1 megohm down to 47 kiloohms. So by reducing the input impedance, I also reduced the input noise. And secondly, I wanted to handle the popping sound that occurred when you went from the affected channel to the clean channel, and vice versa. So even with no signal applied, you still had a popping sound when you went between these two channels. And for this, the first modification that I brought was the driving signal to the transistors. So this RC circuit had its values increased tenfold, both the resistor and the capacitor. This brings a much slower signal into the gate of the transistor. I also removed this source gate resistor. The transistor was switching just fine without it. And finally, I reduced the values of these stabilizing resistors, so R12, 13 and 9. Basically, the purpose of these three resistors is to keep the reference voltage potential in these 3 points around our supply divided by 2. And by decreasing their values, these three potentials are much more stable. So basically, by making these modifications, I went from a very audible popping sound to something that you can barely hear. So final thing to do is actually insert our effect and see what happens. And this is the final board that I came up with. So it's slightly larger than the board that we previously expected. I mean, I extended it on one side and I cut off a bit from the other end. So here at the far end, some of it was cut off, basically because I didn't really need it. All my layout fit into this small area. And we can notice our two large components. So we have our variable resistor and also this huge capacitor. Now this is not the 10 microfarad capacitor that we saw in the schematic, it's an 82 microfarad capacitor. And it's not a normal aluminum electrolytic, it's a polymer electrolytic. Basically, this type of capacitor has far lower ESR, and we'll see why that's important in a moment. But for now, let's just see how this thing fits into the box. Well, there's not a lot of space around here, but it does fit in. It doesn't hit our capacitors because, well, they're smaller this time. And other than that, it fits in quite nicely. The screw holes are aligned. I mean, these are well, we don't really need them, so it's okay. And now, granted, there's a bit of space in between the spacer and the PCB. That's because the spacer could be a millimeter or two longer, but it's okay for now. If I would add in some screws, then the whole board would be in place and nothing would be able to move it. So not much left to do. Let's fire it up and see how this thing works. So what I got here is the effect itself. I have two oscilloscope probes, one connected to the input, one to the output of the effect. And let's not wait any longer. I'll be using my adapter to supply it, and let's see what happens. So we can see that when there's no signal applied, both the input and the output are roughly the same. But now when we apply a bit of signal, we can see our input signal and our output signal. Now there doesn't seem to be that much of a difference, but if I strike the chord really hard, we can see that even with very large amplitudes and quite small amplitudes, the output is fairly constant. So it's not keeping the amplitude perfectly level, but it's doing quite a good job at keeping it at quite a rough ballpark. Now another thing we can look at is how our gain signal looks, so how the peak detector is influencing the gain of our signal. So right now on my first channel I still have the input signal, and on the second channel I'm looking at the voltage from the emitter of the last transistor of the peak detector. So right now we have a very high voltage coming from the peak detector, so this going through the resistor is causing our maximum current, so maximum gain. But now when I strike one of the chords, we can see that our gain reduces, and then it slowly recovers as the input signal is decreasing. So when we have a very high input signal, we don't need that much gain, so the gain is being reduced by the circuit. But as the input signal reduces in amplitude, the gain increases back. So this way, the output amplitude is always kept constant. Now, there's one more measurement I want to show you, and that is the voltage present on my electrolytic capacitor. So the buffer capacitor, that is setting the rate of gain change. So right now my second channel is directly connected to the capacitor, and now if I just strike one of the strings, you can see that as the signal is being applied, we see the voltage on the capacitor dropping. So my transistors are detecting the peak voltage and applying it to this capacitor. Now to get the better reading, I set my second channel to an AC coupling, so we can't see the exact DC value, but what we can see is that the voltage is oscillating. So every single peak has a direct indentation in the voltage on the capacitor, so when the peak is hit, the capacitor is being discharged. Then the capacitor slowly charges up, and then the next peak hits, and again the voltage drops. Basically, when I had the normal electrolytic, this behavior was far worse. And the reason why this is a problem is that this voltage gets modulated into the gain of the amplifier. So in the end, the amplifier doesn't just adjust its amplification based on the level of the sound, it also modulates the sound with the sound itself, so you get a very weird sounding effect. By putting a larger capacitor that has a far lower ESR, this effect is far reduced. So finally, let's have a better look at how the effect is working by playing around with its potentiometers. So first of all, when I turn the effect on and off, you can barely hear that there's a popping sound anymore. So before this was a much more obvious problem, but right now it's more than acceptable. Now if I try to sing something, I can't sing. So this is the normal sound going through the circuit without the effect. Now when I introduce the effect, where we have a much louder sound, but this can be set with one of the potentiometers, so I'm using 3 of the 4 potentiometers. First one that I would like to look at is this 4th potentiometer. This basically sets the output volume level. So if we try it out, we can set it to a minimum so we can't barely hear it. And then if we turn it the other way around, it becomes very, very loud. Now there's two more potentiometers that I'm using. The one on the far right is connected in series with my feedback signal. So basically by setting the value of this potentiometer, I can set the maximum gain current. And this one, if I set it to the right side, then I have the maximum resistance added, so my maximum gain is the lowest. Whereas if I set it to the other end, then I'm increasing my maximum possible gain. This is more obvious when there is no sound, so you'll start hearing some background noise, some buzzing. It's not something you really want, but this makes the circuit very, very sensitive because there's a lot of gain this time. So now even if I barely touch the strings, you can already hear them. Whereas if I go to the other end, you no longer hear it. You don't have that much gain anymore. Now there's one more potentiometer that I'm using, and basically this is connected here in between my positive supply and my capacitor. So basically the lower the value is here, the faster the capacitor can recharge, whereas if it's higher, then it will charge up slower. Basically this is setting how fast the gain can increase. The gain can decrease very fast because of the transistors. They're directly short-circuiting the capacitors to ground, but to charge the capacitor back up, it will take a bit of time. So one of the interesting effects that this circuit produces is that if you play two strings, one that is not struck very hard, so you can just barely hear it, but then you play another string and you struck this one much harder, the volume on the first string will abruptly decrease. That's because the maximum volume can only have a certain limit, so the circuit is amplifying whatever signal it's getting to this limit. So all in all, the circuit works. It's not a very interesting circuit. I mean, it doesn't make a very obvious effect like a distortion, for example. It's one of those effects that you actually need to know what you're listening to actually feel what it's doing, but it's quite interesting from a circuit point of view. But for now, hope you got some useful information out of this. Leave your thoughts in the comments. Thank you for watching. Make sure to subscribe to be up to date with all my latest videos, and see you next time. Bye bye.